Okay, so we have for each observation, we have K predictors, or P predictors, or P variables, P factors, and we'll denote them by X, just as when we discuss the linear discriminant case. Now, remember that we saw earlier that Bayes classifier is optimal. So since Bayes classifier is the optimal classifier, then all we would need to know is to be able to know what the probability of a given group or belonging to a certain group is given the values of X, given the P values, right? The values of the P predictors in X. That's all we need to do, this posterior probability. With this posterior probability, and then we would assign an observation to the group that has the largest posterior probability. Now, if P sub k is the prior probability of class little k, and we have k classes, the sum of P sub k is equal to 1. That means that every observation belongs to only one class, and all the classes contain all the observations. Okay. And if we denote by f sub k of x the probability density function of the observation in class k, in class little k, that's why the little k here. Then, according to Bayes' theorem, the posterior probability that we would need to know to do a correct classification would be the probability that G equals to little k, given the values of X, and that would be the density, the kth density, the density of the kth population times its prior probability divided by the sum of all the densities times their prior probabilities. Okay, that's Bayes' theorem. So that's all we would need to know. Okay. Now, as we did in the linear discriminant case, let's suppose that we model each class density as a multivariate Gaussian distribution. Okay. Let's assume that we model each density as a multivariate Gaussian, so that the kth density, the kth PDF, is given by this expression here, which is the multivariate, the p-dimensional, the p-variate normal distribution. Okay, with sigma being the variance covariance matrix, mu sub k being the mean vector for that kth group. Now, quadratic discriminant analysis, if the sigma sub k's are not equal, then the discriminant function is going to be quadratic, given by this expression here. Again, all we have to do is work with the densities, and we'll arrive at the discriminant function being delta sub k of x equals minus 1/2 log of the determinant of sigma. Here should be sigma sub k. Okay, here should be sigma sub k minus 1/2 of x minus the mean transpose the inverse of the variance covariance matrix for the kth population, x minus mu sub k plus the logarithm of prior probability. Actually, this is the same expression we had for the linear discriminant case, except that there we assume that all the variance covariance matrices were the same. And then the decision boundary for each pair of classes, K and L, let's say, can be described by the equation. It's a quadratic equation. Is the set of all the x's. That's, remember, this is the decision boundary. Okay, so all the x's for which delta little k of x equals to delta sub L of x is the boundary between classes K and L. Okay. Now, since we have this sigma inverse here, and we don't simplify like in the linear case, we end up with a quadratic function of the x's. That's why it's called a quadratic discriminant analysis. This is data that generated. This is simulated data, so we know what the right discriminant function is. Okay, it's generated from 3 Gaussian mixtures. These contours on the left correspond to a 95% highest probability density, 95% highest probability density. Okay, in the 5-dimensional space that contains x1, x2, x1 times x2, x1 squared plus x2 and x2 squared. Okay, that's the left using the linear discriminant analysis within a 5-dimensional space. Here I have the 5-dimensional space is wrong. This shouldn't be here. Okay. So on the left, we have what we would get if we fit a linear discriminant function to the variables x1, x2, x1 times x2, and x2 squared, and x1 squared, and x2 squared. That is, we're fitting a linear discriminant function to my predictors in this particular case are x1, x2, x1, x2, x1 squared, and x2 squared. These are my predictors, and that's the linear discriminant function. So it is a function of the squares of the second order, a second order polynomial in x1 and x2, right? It's a second order polynomial. And these are the boundaries, these are the quadratic discriminant functions, also the 95%, the contours, the 95% contours. Okay, so as you can see, both are separating roughly in the same way. However, it can be shown, and we will see some chart later, that if in fact the variance covariance matrices are different, then the quadratic discriminant function gives better results for classification prediction than the linear discriminant function to apply to a quadratic polynomial of the original variables. Okay. Now, the question then comes, why don't, if a quadratic discriminant analysis is more flexible than the linear discriminant analysis, why don't we use it always instead of using linear discriminant analysis, assuming variance covariance matrices are the same? Well, we could use it. However, we may be, in some cases, we may be overfitting if in fact the discriminant function should be linear. Okay, so there is a trade-off between variance and bias. Oh gee, my translator failed here. This is variance and bias. Okay, there's always a trade-off between bias and variance. And if I use a linear discriminant analysis instead of quadratic discriminant analysis, when I should be using quadratic, I may have more variance and less bias. Okay. But I may, on the other hand, if in a case where a linear discriminant function is much better, I would be overfitting my training data if I use a quadratic discriminant function. Okay. So here on the left, we have a case where this is data simulated from two normal distributions, and with both variance covariance matrices are the same. If you look at the distribution of the blue data points, it looks like this, and the distribution of the yellow data points looks more or less like this. Okay, so it looks roughly similar. Looks like the variance covariance matrix, the variance covariance structure is very similar in both. In fact, it's actually the same variance covariance structure. So in this particular case, the linear discriminant function is these black dots. That's the linear discriminant function. Okay. Base classifier is what are those, like violet dashes, right? This dash line is the base classifier. So that's the base classifier. And the green curve is the quadratic discriminant analysis. Okay. So as you can see, the linear discriminant classifier, which is the blue dot, the black dots, is closer to the optimal classifier, which is the base classifier. But that's a case where both samples are generated from normal distributions. And in this case, with the same variance covariance matrix, in this case, the variance covariance matrices are not the same. You can see here clearly that there is an orientation here to the right in this ellipse, and for the blue dots, it looks like we have this type of variance covariance structure. So we have different variance covariance structure for both populations. And in this particular case, when we do not have equal variance covariance matrices, what happens is that the quadratic discriminant analysis, it's most closer to the base discriminant, the base classifier, than the linear discriminant analysis. Okay. So yeah, it makes sense to use the quadratic if, in fact, the variance covariance matrices are different. Now, there are tests to check whether the variance covariance matrices are different. However, those tests are not that reliable, and they're not very powerful when P is big, when the number of predictors is big. We're talking, if you're talking about P dimensions that with P around 80, which is in many classification cases, we're working with more than 50 predictors, then those tests are almost meaningless. Okay, but there are some tests that you can use with a small, if you have a small number of predictors, that can be done, and most of the software packages give you that. I don't believe that that's critical, because actually linear discriminant analysis is strict, and quadratic discriminant analysis both are very restrictive. Yeah, quadratic is more flexible than linear, but both are restrictive. They assume normal distributions for the predictors, which is not usually the case. Okay, QDA is of course the preferred approach on the two methods. The estimates for QDA, that remember that graph that we showed, where in the left we have the linear discriminant analysis using as predictors x1, x2, x1 times x2, x1 squared, and x2 squared. Those, you can see that those two were very close. Okay, referring back to those two, these two were see this one. These two were very close. Okay, so we could do the linear discriminant analysis and all that, but there's in those cases the QDA, quadratic discriminant analysis, is a preferred approach, and in part of the reason, this is not really the reason, the most important reason, because of computing power, But for linear discriminant analysis, there are k minus 1 times p plus 1 parameters, roughly, okay? Since we only need the distances, we don't need to compute the exact function. We only need to see how far away are the discriminant functions from the little k class to the big K class, okay? So that's all we need. So we need only to estimate k minus 1 times p plus 1 parameters. For QDA, for quadratic discriminant analysis, we need to estimate k minus 1, k is the number of classes, remember, times p is the dimension, times p plus 3 over 2 plus 1 parameters, okay? So in the case of the Karam data that we will work later, we have 85 predictors in 2 classes. So with 85 and 2 predictors, we would need to estimate 3,700 parameters, roughly. Okay, that's in fact not too heavy of a burden with the computing power we have now, but still it's more than the linear discriminant analysis. It's heavier than the linear discriminant analysis. LDA, we already said this thing. The linear discriminant analysis is less flexible than quadratic discriminant analysis, and therefore has a smaller variance, but may have larger bias. If the covariance matrices are substantially different, utilizing LDA will lead us to high bias. Okay, so if we in fact have very different variance covariance matrices, and we use linear discriminant analysis, we may have very high bias. So that's why every case has to be handled in its own. There's no model that fits everything, that fits all the cases, all possible cases. But that's a quadratic discriminant analysis. Yes.
Can you go back really quickly to the previous slides, please?
Yes.
Wait.
Here?
Yes, thank you, teacher.
Okay. Now, as I said, linear discriminant analysis and quadratic discriminant analysis are restrictive because of the nature that is required on the predictors. So we'll look at other methods. One method that's used very often is the logistic regression. I call it here binary for the 2 classes, but if there's more than 2 classes, for more than 2 classes, for more than 2 classes, it's called multinomial regression, logistic regression. Okay, so it's not restricted to 2 classes, but normally binary logistic regression is usually called just logistic regression, and if we are talking about more than 2 classes, we normally use the term multinomial logistic regression. Okay, and this model, logistic regression, is a part of what's called GLM, logistic regression. Is part of generalized linear models. Okay, GLM stands for generalized linear models. Okay, so that's a group of models that include logistic regression and also include linear regression, the way we teach it here in the regression analysis class. Okay, and actuaries use the GLM models to, for example, compute pricing, do pricing for policies and stuff like that. They use a lot of GLM models, although lately it's been shown that some of the machine learning models that we have available give much better results than GLM models, okay? For price computations, for price estimation. Now, again, an observation is assigned to one of the categories according to which of the two categories or three, whatever, is more likely to occur. This is what I was saying earlier. Binary logistic regression is usually known as logistic regression. However, we can have logistic regression with more than two categories. Examples, there are plenty of examples of binary cases: cancer, no cancer, fraud, no fraud, and so on. Okay. Now let's look at the odds ratios. Odds ratios, what are the odds ratios? Suppose we have an event. We have two possible results of an event: success or failure. Okay. And given the probability pi of success, the odds are defined as pi divided by 1 minus pi. Okay, that is the probability of success divided by the probability of failure. Those are the odds. So when the odds are greater than 1, a success is more likely to occur than a failure. Okay. For example, if pi is 0.75, that is the probability of success is 0.75, the odds are 3. That is, the odds are 3 to 1 that will have a success. Or a success is 3 times more likely to occur than a failure. Okay, a success is 3 times more likely to occur than a failure. If pi is less than, if the odds are less than 1, then a failure is more likely to occur than a success. Okay. So greater, if the odds are very close to 1, it means that doesn't matter, right? Success is almost as likely to occur as a failure if the odds are equal to or very close to 1. So odds greater than 1 means that success is greater than, is more likely to occur than a failure. If they are less than 1, then a failure is more likely to occur than a success. Now, for pi is a probability of success, we can think of pi as a parameter of a binomial distribution. For n trials with probability of success pi. So the function g of pi, which is the log of the odds, this is the log odds ratio. Okay, this is the log odds ratio. This is called the sample logit. When I have the sample estimates of the probability pi hat is the estimate of pi. So these are the sample. This is called the sample logit because it's the sample estimate of the log odds ratio. So this would be the log odds ratio. Okay. So G of pi is it's called the sample logit. It is logistic regression has been very common model for a long time. It's been used a lot in medicine. It was used a lot of banking. It's now being replaced by other methods. It was used very much for credit scoring and stuff like that. In medicine, definitely it's used a lot. It's still used a lot. Social sciences, in business and genetics, in any area where there's classification, a classification issue, a prediction, it's normal to use the logistic regression model. If the response is binary and the predictor is X, which has p variables, is a p-dimensional vector, then pi of X will be the probability that Y belongs to class 1 given X, and that's 1 minus the probability that Y equals to 0, that Y belongs to class 0. Okay, for example, Y is equal to 1 means cancer, then that will be the probability of cancer given X, the indicators of the health of the individual, and y minus the probability, and it's equal to 1 minus the probability that doesn't have cancer given x. For once only for a single predictor, if p is equal to 1, if little p is equal to 1, then pi of x, the probability of y equal to 1, this is the thought we're going to be using. Pi of x will denote the probability that y belongs to the first class, the class of interest. We normally call the classes so that the class of interest is 1 and the class that doesn't interest us is 0. Okay. Pi of x, the probability, the conditional probability of y equal to 1 given x, is the exponential. This comes from the logit expression, the exponential of alpha plus beta x divided by 1 plus exponential of alpha plus beta x, in the case that p is equal to 1. Okay. If p is equal to 2, then we would have pi of x will be the exponential of alpha plus beta 1 x1 plus beta 2 x2 divided by 1 plus the exponential of alpha plus beta 1 x1 plus beta 2 x2. Okay, and so on for p is equal to little p in general. But this, for the particular case where we have one variable, it's easy to explain graphically what happens with the model. The logit is the log of pi of x divided by 1 minus pi of x. We saw that. That's the logit, and that's alpha plus beta x. So the logit, that's why the logistic regression is considered a linear model. Because if you see here, the logit is a linear function of x. We have a linear function of x, linear function of the parameters and so on. So the logit is considered a linear classification model. But there is, in fact, we do not have restrictions on what x can be. X can be continuous, x can be discrete. Doesn't matter, can be categorical. The interpretations change depending on whether the variable x, the predictor, a certain predictor is continuous or categorical. Okay. What's the interpretation of beta, of the coefficient in pi of x? The sign determines if the posterior probability, the probability of y equal 1 given x, is increasing or decreasing in x for a single value for a single independent variable, a single predictor x. The rate of growth is the absolute value of beta, okay, the rate of growth or decay, right? Because if it's positive, it'll be the rate of growth. If it's negative, it'll be the rate of decay. So the function would look like this, or it will look like this. And the sign of beta, here beta will be greater than 0, and here beta will be less than 0. And this is the rate of decay is the magnitude, the absolute value of beta. And here is bounded by 1 and 0. Okay. So it tells us if it's increasing, if the probability is decreasing or increasing with x. If you recall, the logistic density function is symmetric. Okay, so pi of x will go to 0 at the same time, the same rate that it goes to 1. So it tends to 0 at the same rate as it tends to 1 because of the symmetry of the logistic density function. Now, remember that we said that pi of x divided by 1 minus pi of x is the exponential of alpha plus beta x. And that's exponential to the of alpha times the exponential of beta to the x. So the logos are multiplied by e to the beta for every unit of growth in X. If X is continuous, then for every unit that X grows, the log odds are multiplied by e to the beta. If I go from X equal to 1 or to X equal to 2, and X is continuous, then the log odds will be multiplied by e to the beta for every unit that I increment X. Okay, the log odds are multiplied by e to the beta. So this interpretation is very useful in logistic regression, and that's why logistic regression is a method that's preferred by a lot of people because of the interpretability of the model. And we'll look at an example now. So inference regarding regression, one is we saw that the logit is the logit of pi of x is alpha plus beta x. Okay, what will be the sample logit? The sample logit will be the estimate, replacing the alpha and beta for their estimates. Okay, so if you look at this case when p is equal to 1, one interesting case here, one interesting test is whether or not beta is equal to 0. That is, the coefficient of x is equal to 0 or not. If it is equal to 0, this is equivalent to the independence hypothesis. You see, if beta is equal to 0, it means that pi of x, the probability that y equal to 1 given x does not depend on x. Okay, if beta was equal to 0. Because if beta was equal to 0, then the logit will be simply alpha. Okay, and therefore y, the probability that y equals to 1 given x, which is pi of x, is independent of x. It doesn't depend on x. So that's the beta, the null hypothesis that beta is equal to 0 is the hypothesis of interest because it's the hypothesis of independence. To test that hypothesis, we normally use the Walsh test, which is sort of the standard test. We take the sample estimate of beta divided by its standard error, and under the null hypothesis that beta is equal to 0, z squared has a high square with 1 degree of freedom. See, the z squared is a high square with 1 degree of freedom. In other words, under the null hypothesis, z would be normally distributed, approximately normally distributed. And the confidence interval for beta is computed using this Walsh test as the percentile from the normal distribution times the standard error. Okay. So a 95% confidence interval for beta would be beta hat plus or minus 1.96 times the standard error. Okay, the standard error of beta hat. And we use the normal distribution also, or the t distribution, if we have very few degrees of freedom, to test this null hypothesis that beta is equal to 0. And the confidence interval for the logit is simply alpha hat plus beta hat x null plus or minus the standard error z sub alpha over 2, the percentile from the normal distribution, times the standard error of the estimate given x null. Okay. So that when we look at the output in R, when we look at the hypothesis, the p-values that we'll see there refer to this hypothesis. Okay. And we can use the normal distribution to construct a confidence interval for beta, or the t distribution if we have very few degrees of freedom. which in most of the cases we'll be dealing here, we will not have small number of degrees of freedom. We'll usually have large number of data points. Any questions so far?
No, teacher.
Okay. Let me raise this line here. Oops. Cannot erase it. Anyway. What assumptions do we have to be able to train a logistic regression model? One is the target is to use binary logistic regression. Okay, for binary logistic regression, the target is binary. The target is binary for binary logistic regression. Now, there are one or more predictors, and they can be continuous or categorical. Okay, when they are categorical, the levels of that predictor are called the group levels. Okay, if one of the predictors is ordinal, for example, measurements in a Likert scale, or they can be treated as continuous. We've seen that before. In Likert scale can be treated as continuous as long as we have a scale of 7. If we have a scale of 4, that's going to be, that's in some cases, for example, linear discriminant analysis, you can treat it as continuous, but it will not work very well. Okay, because that's too far from having normality. But here we do not assume normality. The observations must be independent. And the target variable must be mutually exclusive and exhaustive, right? The same as usual. We must have at least 15 cases for each predictor. Okay. In fact, it's very, very seldom nowadays we have such scarcity of cases. It happens in the medical field. Sometimes it's very difficult to have larger sizes of a larger number of patients, for example, participating in a trial. But in general, at least 50 cases for each predictor would be advisable. Okay. And there must be a linear relationship between the continuous predictor, not the categorical, just the continuous predictor, and the log rate and the logit transformation. Okay. Okay. Remember, the logit is expressed as a linear function of the x. Okay. So there must be some sort of linear relationship between the logit and each of the continuous predictors. There are several tests. Again, our emphasis here in this class is not on testing hypotheses, but there are tests like the Box and Tidwell test, which aggregate interaction terms among the continuous predictors, okay, and their logarithms to the regression equation. But that's we will not get into that. Our focus will be determining the best model to predict, and then train that model, fine-tune it, and use it. There's another assumption: we should not have multi-collinearity among the continuous predictors. Okay, that is, if we have two predictors that are highly correlated, two continuous predictors that are highly correlated, we need to eliminate one of them. Okay, or we need to run first a principal component analysis to eliminate collinearity and work only with the main principal components. This is another alternative. Okay. And we use the correlation matrix that we've seen before, the heat map, to evaluate this if we have an issue with multicollinearity. We can also use the variance inflation factor values that are calculated by a lot of the software packages. There should be no extreme outliers, and there should not be any highly influential observations. Okay. If there are outliers, it's not okay just to throw it away. We need to find out if there's a reason for that outlier. And in some cases, if we find, for example, let's suppose that I have an outlier because I'm trying to predict the results of a manufacturing process. And one of the predictors, I have three predictors. I have viscosity, I have that's oil viscosity, temperature, and pressure. If I have those three predictors, and then I have a very influential observation or an outlier, and it turns out that occurred because my temperature gauge broke down. Okay, what if there's a couple of observations where the temperature gauge broke down? Then there is an explanation for that observation, that very extreme observation. I have a temperature of 0, when in fact my temperatures were in the 150 and 200 degrees Fahrenheit. Okay. Well, then that we know that there's a reason for that outlier, and instead of throwing away the observation, we could impute the value of the temperature for that particular observation using something like a nearest neighbors approach, which we'll talk later about the nearest neighbor approach. Okay. Now let's look at an example. Let me see first here, and let me erase this drawing. This is the heart disease data that you already worked out.
Teacher,
Yes.
what did you say that we have to do if we have an outlier? We should not throw it away, but what?
We always investigate what happens.
Okay.
If we're an outlier, we need to investigate what happens. Maybe it's a mistake and we eliminate the observation. Okay. Could be an observational error. There are other cases like the one I described where a measurement device broke down and I have my data are all concentrated around certain value in the 100 and 200 degrees Fahrenheit, and I have an observation that has a 0 there. That observation is an outlier and maybe also influential. Okay. Now, if I found out that's what happened, and in this case where I had viscosity, I'm going to make a chart easier. Let's see. Suppose I have viscosity and temperature, and I'm measuring the hardness of an end product. And I have my data looks like this. And I have one data point that's here. Okay, in 0. Well, all my temperatures are over there. Well, that's an outlier. Now, what can I do in this case? This outlier, if it's a mistake, I'll just remove it. Okay, if it's a mistake, I'll just remove it. But if I know that at the time that this measurement was taken, the temperature gauge was broke down, and that's why you have a temperature of 0, I can impute the value and I say, okay, I look at the nearest neighbors for that observation, and maybe these are the near neighbors of that observation, and I say, well, that I'll estimate this temperature to be this one here. So I'm doing imputation to replace an outlier by an observation that seems to be more reasonable based on the fact that I know that there's a physical reason why I don't have that measurement. Otherwise, we would need, if there's no explanations on, we probably need to throw that outlier out, because I shouldn't have outliers for the analysis. But if I know a reason, I need to consider that, because there's outliers that are informative and there are outliers that are not informative. And an informative outlier is the one that's giving me information about the process. Maybe there's something around that happened around that time, or what that happened with a customer in their credit card use that made that customer do something weird. Okay, that's an information outlier. I have to treat that apart. I cannot include it in the same model because there must be a reason for that outlier. Okay.
Okay.
There are cases where we can impute the value.
Okay, thank you.
So we'll look at this example, and we need to find if heart disease incidence can be predicted based on age, height, gender, and maximum aerobic capacity, VO2 max, that's an indicator of physical condition and health. We have 100 people where they perform aerobic capacity tests, and they measure their characteristics. Then each subject was evaluated to determine the presence or absence of a heart disease. We have a total of 100 people. The data are in file heart disease, .csv. And what I'll do now is let's switch to I'll review this part first, and then we'll go over the R script. So I'm going to use caret to create a data partition. Training rows, I create my data partition with 70% of the data. So I'm going to use 30 observations for training. I'm going to use the 70 observations for training and 30 for testing. And I split my data set the way we've been doing so far. I look at my proportions. I see here that the data is not balanced. That is, I have more cases, a lot more cases of non-heart disease than the cases with heart disease. And because I use the create data partition function, I maintain the proportions roughly the same in the training set and the test set. To fit a linear regression, logistic regression model, we're using the function GLM. GLM stands for generalized linear model. So we'll use the GLM function, and I specify the formula. I'm saying heart disease, which is my response, HD as a function of the rest of the variables in the file. Then I specify the family, because the family could be multinomial. If I have more than 2 classes, the family would be my multinomial. So I'm specifying that the family is binomial because I only have 2 classes, heart disease or not heart disease. And my data is going to be the training data. So I'm going to feed the model. I'm going to train the model with the training data on. And then I get these results. Deviance residuals, we'll talk about deviance in a few minutes. And then we have the estimates of the coefficients, their standard error, the z-value, okay? And this is the p-value. So this here is a p-value for which test? In this case is for the test that the intercept equals 0. In this case is for the test that beta 1, sorry, that beta 1 equals 0. versus the alternative that beta 1 different from 0. Okay, and so on. This is the test for beta 2, for beta 3, and so on. So those are the tests for the coefficients of the different coefficients of the model. The coefficient for age, the coefficient for weight, for gender, for VO2 max, which is the heart rate at in a stress test. Okay. As you can see, I have a categorical variable here, gender, and I have age, which is continuous, weight continuous, and VO2 max, which is continuous. Apparently, the only significant variable here is age. So the coefficient value is 0.06. That will be the beta 1, right? The beta 1 estimate is 0.06. And this appears to be the only significant parameter there. Okay. Now let's look at let me take this chart here. I'll explain. There's something here called the null deviance and residual deviance. I'll explain that with the next analysis of variance. I'm going to run an analysis of variance for this regression logistic regression model. And the test we're going to be using here is a chi-square test. This is different as the analysis of variance for linear regression model. Okay, this is different. What we analyze here is what is the deviance. There's something called the null deviance, the null residual deviance. Okay, so the null residual deviance is the deviance, or how much is explained by just a constant in the by the full model. Sorry, by the full model. So if I include the full model, what is all the variability that explains the model? That's 92.122. Now, every time we add a factor, it's telling me how much that deviance is reduced. So if I reduce here, I'm reducing the deviance. I put the explanation here. The neural residual, the model performance, that shows the model performance. And let me erase these lines here. We have a model that contains the constant term. That's the null. That's with the model with only beta null. The only beta null. That's why they call it the null. And it has a constant. And now, so that if I just try, imagine that in a linear regression case, you fit you have this data. Just imagine, this is not the case, but imagine a linear regression case where I just, instead of feeding a line there, I just feed a constant. Okay, if I only feed a constant, there will be a lot of variability that is not explained by the constant. Okay, that amount of variability that is not explained by the constant is measured by the residual deviance for the null model. If instead now I add a variable, and instead now I add the variable x there, and I fit this thing, then there's variability that I do not explain with that line that's still left. But what this measures here is how much I reduced this deviance when I included the variable age. So when I include the variable age, that I get a reduction of 5.07 units in deviance from the origin, from the constant only. Okay. If I add now the weight of the person, the weight of the individual, that it reduces the deviance even more. That reduces the deviance in 8.87 units. So that's now I bring deviance to 78.171. So this is significant at the 5% significance level, and this is significant at the 0.01 significant level. Okay. So the ANOVA and the analysis of variance table tells me that I should consider these two variables. Okay. The rest, the other variables, when I add them to the model, they're not helping me reduce the deviance any further. And this is the p-value for using this chi-square test to see if the deviance was reduced enough. Statistically, if the deviance reduction is statistically significant. Okay, so this table is important for that, because if we only look at the other table, we may only look at the age as a factor. Here it's telling me that I should consider also weight. Okay, now I say that here the table shows the reduction in deviance when we add each variable to the model, and the variable session weight achieve a significant reduction. They achieve a reduction of 13 in both together, about 13, whereas the next one is VO2 max, which reduces only by 2, and it's not significant. Okay. So I can now feed the model with only these two variables, age and weight. Okay. And I added here another explanation. Large p-value indicates that a model without the corresponding variable explains about the same variability as the model with that variable. So why add a variable? Because of parsimony, there's no need to add a variable that doesn't have value. Okay. In essence, that's what it's saying. Okay, now in regression analysis, there's what we call the R-square. In regression analysis, R-square is the coefficient of determination. The R-square has an interpretation in linear regression, and it measures the percentage of variability that is explained by the linear regression model. Okay. Well, there is no R-squared in logistic regression, but there is an index, well, that was developed by McFadden, and this is the equivalent of the R-squared for logistic regression. It reflects the optimization criteria that we use in logistic regression, as well as the variance that is explained by the model. Okay. This is the way it's computed. It's LL full is the log likelihood of the complete model. Okay, it's a log likelihood of the complete model, and the LL null is the log likelihood of the model with only the constant term. Okay, so the McFadden index is 1 minus the ratio of the log likelihood of the complete model divided by the log likelihood of the model that only contains the constant term. And then the index is adjusted to penalize for the number of predictors, because the more like in the case of linear regression, I can add predictors and I keep increasing the R-squared. And in linear regression, there's something called R-squared adjusted, or adjusted R-squared. And that's adjusted for what? For P, for the number of predictors. Because the more predictors I add to a regression model, the R-squared will always increase. Okay. So what we need as a guidance is something that considers also the fact that the coefficient of determination always increases, if I add variables. I need to penalize the model somehow because of I'm adding more variables. So we adjust it by subtracting the number of parameters, the number of predictors here in the numerator. In this case, we get a McFadden index of 0.18. There are no tables for what the McFadden index, but empirically it's been shown that a McFadden index between 0.2 and 0.4 indicates a reasonably good model. Okay, so a McFadden index between 0.2 and 0.4, it means that we have a reasonable model. Okay. In this case, we have it's not that good, it's 0.18. Okay, the McFadden index is 0.18, but we'll take it as close enough. Okay, it's this logistic regression model is not very good for this case, as we'll see later when we look at the different models for this same data. Now, to assess the predictive model of the model, the predicted capability of the model, we use the function predict, just as we did in the linear regression case, with the parameter response to obtain the estimated probabilities of belonging to class 1 or class 2. The default boundary is 0.5. It doesn't have to be that. We can change that because we get the probabilities, so we can change our boundary. And we can calculate the ROC curve and the confusion matrix. And another criteria that we could use, particularly when the data is not balanced, is the area under the ROC curve. As the confusion matrix, we have an accuracy of 0.7. Is not that great. Sensitivity is very poor. Sensitivity is around 0.5, and specificity is 0.8. Now, if I wanted to increase sensitivity, what would I have to do? Suppose I wanted to increase sensitivity. Anybody? Do I have to increase the cutoff point, the boundary, or decrease it?
Decrease it, right?
Yeah, you have to decrease it, Cecilia. That's right. Okay. If we decrease it, we can get better sensitivity, and we will lose on specificity. That's the ROC curve. Okay, an area under the curve of 0.67 is not good. Okay, remember that an area under the curve of 0.5 is like flipping a coin, so it's not a very good area under the curve. But anyway, let's continue with this model, although it's not a good model for this data, but so that we can go over the interpretation of the results. Okay. I'm going to fit here. I'm fitting only age and weight. Age and weight. Okay. Now, we normally interpret the exponential of the coefficients, because the exponential of the coefficients tell me, for example, in the case of a continuous variable, the log odds for what is the value that we multiply the log odds for every unit increment in x. Okay, remember we said that earlier. So the log odds is this one here, is beta 0 plus beta 1, is the exponential of beta e to the beta 0 times e to the beta 1 x1 times e to the beta, here should be beta p xp. So according to this model, what we have is what? According to this model, the odds of a heart disease, of a heart disease increase about 6.5%. Why 6.5%? Because the exponential of age is 1.65. Okay, so it's greater than 1. So my odds to have a heart disease, the odds of having a heart disease increase by 6.5% for every unit of age that's increased. So if age is in years, for every year that I increase in age, the odds of having a heart disease are increased by 6.5%. By 6.5%. And that will be the interpretation. And now look at the weight. The weight is 1.63. Is 1.0637. Okay. So for every kilogram, assume that weight is in kilograms or in pounds, whatever. If it's in kilograms, then for every kilogram of weight that the individual increases, his or her odds of having heart disease increase by 6.4%, roughly. So we interpret the exponential of the coefficients. That's what we interpret in the logistic regression model. And it tells me how each variable is impacting the odds of having a heart disease. Okay. And that's what we use for interpretation, the exponential of the coefficients. Okay. And I'm going to stop here. We'll go over the script next class because I didn't give you the middle break. And if you want to turn on your cameras, that'll be nice to see some faces. And tell me if there are any questions, and we'll go over the script next class.
I don't have any questions.
No questions? Okay. Well, any of you did something interesting over the long weekend? No?
Yes, I did.
Where did you go, Farid?
Oh, tranquilo.
I visit my family in San Miguel de Allende.
Oh, that's good. That's good.
Yeah.
4 days was a good long weekend. Huh? Anybody else? Or did you study a lot? Yeah, I see some smiles, so maybe you did study a lot.
No, teacher, only, well, in my case, I only eat a lot and gathering with my family also.
Oh, that's good. Yeah, enjoying your family. Okay, well, that's great. Well, I'll see you next Monday. Run what I used to do with the schizophrenia data, and then we'll go over the script for the logistic regression next class. Okay, and I'll see you. Have a nice week. Enjoy it, and we'll see you next Monday.
Thank you.
See you next Monday.
Thank you.
Thank you.
Nice
Thank you, teacher.
Bye.
Bye.
Thank you.
Bye. Bye. Thank you.
Bye bye.